start with the problem definition, current and future trends in the field of piezoelectric converters, flexible piezoelectric energy harvesting and sensing elements, nanostructured elements, and perspective and future work. We are all aware about worldwide efforts to gain alternative energy from the surrounding environment and the natural sources like sunlight from solar heat, wind flow, geo and hydrothermal energy. However, all of them require large technical infrastructure, and sometimes it is just not necessary. For example, for the portable and smart electronic devices, which require few tenths microwatt power supply, there is something else which is most important, like compactness, portability, and keeping the size of the power supply as small as possible without to lost efficiency. So one of the mechanisms to gain electrical energy from mechanical vibrations, pressure, force, accelerations, etc. It relies on piezoelectric effect. I will not go deep into the piezoelectric effect in general. Here I just only make a link to the next slides and show some common vibrational sources that could be used in this case. They are related to human motions, to transportations, and to weather conditioning systems and climate change. So here I give some examples about more sophisticated applications of the piezoelectric nanogenerators used as alternative energy sources. Most of them are built on plastic substrates, and they could be wearable or following specific curves and certain shapes. Most of them are applied for personal electronics, portable electronics, automotive industry, and most of them most important in biomedical industry. So they need to be sensitive to weak activation stimuli in order to give sufficient electrical energy to recharge the battery and serving as self-sustainable elements. But still, because of their small thickness and small activating area and volumes, these devices are considered insufficiently efficient. They could give only few microwatts electrical power. So most of the suitable piezoelectric materials are also ferroelectric, so they can be used not only for pressure sensor, but as well for temperature sensor due to their pyroelectric response. So they could serve not only as a harvesters, but they could also serve as a sensors. So you can combine two functionalities in one single devices: sensing and self-sustainable power supply of this sensing part. And broadening applications could be ambient temperature and atmospheric pressure detection, human motion detecting sensors relying on infrared, vibrational diagnostic of equipment condition monitoring, etc. Here, more sophisticated application of the piezoelectric, this time not as a harvesting, but as a sensor. The most important application that will, boost the market in the near future, this would be the biomedical implants that could be implemented in the body organism or could be outside attached as a wearable elements, but still they have to track the natural motions of the organs and to measure regularity of their motion as an indicator of the health condition, and in the same time to be power supplied from this motion. So the topic is really interesting. I have extracted some data about the publishing activities in the last few years with keywords piezoelectric energy converters. And you can see the trend continuously growing up the numbers of papers. And here for the 2021, despite it is only second month from the year, there are already available 600 papers published about this topic, most of them research papers. So the basic requirements to the energy harvesting elements, they have to be compatible with the plastic substrate. I mean, to be able to be produced at low temperature processes. To keep the plastic substrate from overheating and degradation, to be able to compose, build composition between oxides and polymeric piezoelectrics to combine the positive features of both partitions, and to be able to vary the thickness from nanoscale to microscale in order to control some important parameters like efficiency and stability. To the sensing elements, some of the crucial requirements are to be compatible with the MEMS microelectromechanical system technology. It means conventional vacuum sputtering and photolithographic patterning process, and to be able to be nanostructured to increase their surface to volume ratio in order to improve their sensitivity or efficiency by producing nanorods, nanotubes, nanodendrites, and different nanoformations with controllable size and nanoscale level. But currently, there are not yet available sufficient information about how the substrate type is influencing electrode materials, their patterning, their hybrid type ratio and deposition process, how all this affects on the coating, nanostructuring, and how all this affects to the electrical parameters. So in our studies, we used as a flexible substrate plastic substrates from polyethylene naphthalate and polyethylene terephthalate for the harvesting technology. And for the sensing technology, we used deep anisotropic etched silicon substrate. So in this way, this middle square part is converted from solid silicon piece into a flexible silicon micromembrane that could be moved and deviated at supply pressure. And on top, we grow our piezoelectric films. So the starting point is how to replace the classical lead zirconium titanate, PZT, with eco-friendly one with lead-free material. And we started with potassium niobate. It is lead-free, could be grown in form of thin films by radio frequency sputtering in vacuum, and it exhibited stable behavior at multiple bending, which is really favorable for harvesting purposes. Here it is show what is the relation between deposition rate and some deposition parameters like plasma power and plasma sputtering gas pressure, gas sputtering pressure. And here some atomic force microscopic images showing the surface roughness and how it is related to the deposition conditions. So we succeeded to produce a surface which, according to the IFM measurements, is 2.7 nanometers RMS surface roughness, really smooth. It is helpful to attain 400 millivolts and 5 microamperes electrical parameters, which is really good considering the whole thickness of the element, which is not greater than 1 micrometers and area of 4 square centimeter. So after 1,000 cycles of repeating bending, we found that the voltage decreased with 2.2%, which is really stable. And two-dimensional AFM images analysis showed that the microcrack appearing are less than 10 for a scanned field of square almost 200 micrometer inside, and the depth is 190 nanometer, which considering the total thickness of the film is not really a great depth. So the films are really stable, and here is the electrical signal that could be extracted when you mass load the samples at 3 kilograms. The signal is clear, without any spikes, with great periodicity. And by controlling the deposition conditions, we succeeded to decrease the contact resistance to 19 ohms, which is favorable for the interface and contact conditions with the electrodes, helpful in addition to achieve high piezoelectric coefficient greater than 250 picocoulomb per newtons, which is actually untypically high for lead-free and non-nanostructured coatings. And this is the main advantage of the proposed energy harvesting. The same approach we used to optimize the zinc oxide doped by gallium. The function of the doping element is to increase the electrical conductivity and in this way to gain further the generated electrical power without to distract the piezoelectric properties and polarization effects. Here I also provide the different AFM images to compare the roughness of the surface and how it further affects on the piezoelectric coefficient. Actually, it is low frequency element that we succeeded to produce at a highest possible sputtering voltage of the plasma, 1.1 kilovolts. The roughness of the film is nearly 6 nanometers per total thickness of almost 100 nanometers. It is a low frequency element suitable for sensing applications. It exhibits good linearity, error of the deviation of the linearity less than 2%, and reacting in the range from few to 800 grams. The next promising material is the barium strontium titanate. We found for this material that it is susceptible to nanostructuring if we grow it up on conductive polymer like polyethylene dioxide thiophene. It is amorphous conductive polymer. And such kind of nanodendrite shapes are revealed, but it makes the reveal the total surface, which increased the capacity. And although the total film thickness is again less than 500 nanometers and the area is 3 square centimeter, capacity of in the range of few microfarads were achieved. The structure is relatively stable, near 32,000 bending cycles. The capacity is still not greater, variated greater than 70%. Again, it is favorable for as well for harvesting and sensing application, but this time the dielectric losses measurement show that up to 14 kilohertz this element could be applied. It means it is not only low frequency, but extended to the middle to high frequency. It depends on the nature of the material and dipole formation mobility. However, some spikes in the electrical signal appear that need to be carefully processed from the power conditioning system. They are due to the point contact from the non-uniform dendrite structure of the functional film. But still, satisfactory results about the voltage of nearly 800 microvolts and electrical power gain to, let's say, 2.3 microwatts per square centimeter. Comparing with the literature available for this topic, it is a good value, especially considering that the contacts are not from the classical metal layer. Moving next to the piezoelectric polymers, polyvinyl didenfluoride, called trifluoroethylene. It is ink, in form of ink, so it could be screen printed in form of a layer. And we compared the different metal materials and metal patterning shapes, how they affect to the piezoelectric voltage and the stability. So it seems that silver is most favorable in terms of piezoelectric voltage. Next is the gold, and the poorest results we obtained for aluminium. Of course, the shape is also crucial. Although less voltage is generated from the side clamp patterning, we found that it is really stable no matter of the kind of metal material, mostly because the piezoelectric polymer is mostly sticked to the plastic substrate rather than to great area, big area of the electrode itself. Wetting ability of the ink is also important for the performance of the element. It seems that good wetting ability is exhibited to the gold coated pen substrate. So that's why for the gold coated substrate, the cracking were revealed very late. So here are some comparatively tables about the all 9 cases, and it is really compromise between the nature of the metal electrode and the patterning. But in any case, aluminum electrode should be excluded from this competition. The next slide is devoted to the nanostructuring of piezoelectric film, suitable approach to increase the functional area by keeping the total area of the device small. It was found that zinc oxide and gallium doped zinc oxide were more susceptible to nano branching and nano leafing and nano formation by using seed sublayer from conductive polymer in comparison with the barium, zirconium, and strontium titanate. Well, here the advantages is that the different geometrical size available in this nanostructure is able to capture variety of frequency and broaden the working frequency range of the device, which is not possible when you use dense film. In general, the voltage could be increased with almost 300 millivolts, which is also advantage when we compare with high density layer, which is not structured. The Polymeric bottom electrodes still keep the linear dependence between the voltage and the mass loading, although it is less conductive. So it is suitable to work as a sensor, not only for dynamically change mass loading, but also for static strain loading, although it is a little bit nonlinear characteristic here. And we believe that we can further improve the picture by orienting all nanostructure in single axis. That's why finally our last study is for building an array and matrix from nanoporous anodic aluminum oxide with controllable length and diameter of the pores. And we provide that hollow tubes, nanotubes, are deposited from this material, and we started to fill in the tubes by sputtering two-sided from the top and back side in order to fill this tube to produce nanowires from the potassium niobate. Here are the scanning electronic microscopic images of top view of the pores at different filling stage, different filling degree, from open to intermediately filled to fully filled. And here is the cross section of the produced nanowires. Elemental scanning along the tubes shows that uniformly distribution is available of all components. So it is demonstrated that it is not distracted distribution of the component, and linear dependence from the nanowire length. Again, twice improved piezoelectric voltage, and also detected some pyroelectric coefficient, which is not so sensitive from the length of the nanowires, but still it allows combining two functionalities in one single device, pyroelectric and piezoelectric. So as a conclusive remarks, I would mention some perspectives and future work in general, not only in our group. New piezoelectric materials will be developed for high power applications, because currently the low power applications are well covered. The medical industry, in my opinion, will boost further the development of these devices. Next generation commercial devices will be fully wearable and fully implantable. Some problems still need to be resolved regarding the adaptability and durability, especially when the question is about the shape and size that have to be customized. And in the case of healthcare industry, it should be even personalized. And in the context of the present pandemic situation with COVID-19, I found that the functionality offered by these piezoelectric converters are slightly shifted and transformed into sensing abilities for virus detection by using surface acoustic waves devices. Thank you very much for listening to me.